Have you ever been, like, balancing your checking account and you just keep seeing this persistent, tiny mathematical error?
Oh, yeah, the numbers just refuse to add up.
Right. You run the calculations 3 or 4 times, and for this, like, brief, glorious second, you think, wait, maybe I didn't make a mistake.
You start thinking you just discovered a completely new form of currency that miraculously deposited itself.
Exactly. You hope the established rules of finance have suddenly bent, revealing some hidden mechanism working in your favor.
But then, inevitably, you look closer.
Yeah, you realize you forgot to carry a 1 or missed an auto-renewing subscription, and reality sets in. The math was right all along. Your accounting was just flawed.
It always is.
But that specific dynamic, that feeling of hoping a persistent error, means you've discovered something revolutionary, only to realize the established rules actually hold true. That is exactly what particle physicists have been living through for the last 60 years.
It really is. It's a fascinating situation.
Today, we are looking at how a famously rebellious particle just got put firmly back in its place.
Yeah, it's a story about the limits of computation, the psychological weight of theoretical physics, and really what happens when the most precise measurements in human history clash with our mathematical models.
So we are doing a deep dive into a May 2026 report from Science Daily. And this details a monumental breakthrough published in the journal Nature, conducted by an international team led by physicists at Penn State.
It's a massive paper.
It really is. Our goal for this deep dive is to understand a tiny subatomic particle called the muon, examine why it seemed to be breaking the known laws of physics, and explore how a colossal supercomputer calculation finally solved this decades-old mystery.
To really frame the scale of this mystery, you have to consider the standard model of particle physics.
Right.
As far as we currently understand, the universe is governed perfectly by 4 fundamental forces. You have gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. And the standard model is this mathematical framework that unites 3 of those forces, leaving out gravity, of course.
Because gravity always ruins the math.
It really does. But the model explains almost every physical phenomenon we can observe. It is, arguably the most successful scientific theory ever constructed.
Wow.
But there was this single heavy particle that just refused to align with the math.
Okay, let's unpack this.
Yep.
The troublemaker at the center of this controversy is the muon.
Right, represented by the Greek letter mu.
Right. And for you listening, the easiest way to visualize a muon is basically as a heavier cousin to the electron.
That's a good way to put it.
It carries the same electrical charge, behaves very similarly to an electron, but it's like roughly 200 times heavier.
Yeah, and it's also incredibly unstable. It only exists for a fraction of a second before decaying into lighter particles.
So it's heavy, it's unstable, and the controversy surrounds a specific property of it called its magnetic moment, right?
Yes. The magnetic moment is basically a measurement of how strongly the muon acts like a tiny bar magnet.
Okay. According to quantum theory, the math here should be pristine. The standard model predicts that this magnetic moment value should be exactly 2.
Exactly, 2.
Exactly. It represents the precise relationship between how the particle spins or wobbles, really, and the magnetic field surrounding it.
But the physical universe is messy. When physicists actually ran the experiments, they kept observing this slight shift.
Yeah, the value was not exactly 2.
Right, and this tiny deviation became known as the anomalous magnetic moment, or G-2.
And the mechanism causing that shift, it lies in the nature of empty space itself. Because a vacuum is not a void.
Wait, really?
Yeah, empty space is actually this bubbling soup of virtual particles constantly popping into existence, living for a billionth of a second, and vanishing.
Yeah, it's so weird to think about.
I know. But while they temporarily exist, they interact with the muon.
Okay, to visualize this, think of the muon as a heavy spinning top rotating on a table. Based on its weight and velocity, you expect a very specific, predictable wobble.
But this top is wobbling uniquely off rhythm. Because the room is actually filled with invisible quantum dust, these virtual particles you mentioned, just constantly bumping into the top and subtly altering its spin.
That's a perfect analogy. And the key to the muon's specific anomaly is its mass.
Because it's so heavy.
Exactly. Because it's 200 times heavier than an electron, it requires vastly more energy to create. But that same mass makes it uniquely sensitive to interacting with much heavier, rarer virtual particles.
Oh, I see. So an electron is just too light to hit those massive quantum bumps.
Yeah, an electron is simply too light to regularly interact with those massive, fleeting quantum fluctuations. The muon's mass turns it into a highly sensitive probe for the deepest, strangest layers of the quantum vacuum.
And for 60 years, physicists have been trying to precisely measure this wobble. And these are not like tabletop experiments in a high school lab.
Oh, no, not at all.
We are talking about firing beams of muons at nearly the speed of light through massive superconducting magnetic rings.
Yeah, these are huge operations. These experiments started at CERN in the 1960s. Then they moved to Brookhaven National Laboratory, and most recently took place at the Fermi National Accelerator Laboratory.
And the precision achieved by these teams was so staggering that they actually earned the Breakthrough Prize in Fundamental Physics.
Which is a huge deal.
Yeah. And for decades, the experimental measurements from those massive rings consistently disagreed with the theoretical predictions of the Standard Model.
And when the most precise, heavily vetted experiments in the world continually contradict the established mathematical model the scientific community pays attention.
Naturally.
The persistent gap between the physical measurements and the math suggested the Standard Model was incomplete. It fueled the hope that the muon was interacting with undiscovered particles, or maybe an entirely new, hidden fifth force of nature.
But wait, if these physical experiments were so meticulously executed and verified, the obvious question is why theoretical physicists didn't just update the math.
That's the logical next step, right?
Right. Like, if we know the quantum dust is affecting the wobble and we have the Standard Model equations, shouldn't calculating the theoretical prediction just be a matter of plugging the known forces into the formula and running the numbers?
Well, what's fascinating here is that calculating the theoretical side of this interaction was bordering on impossible.
Really? Why?
Due to the behavior of the strong nuclear force. The virtual particles bumping into the muon aren't just simple electrons or photons. They include quarks and gluons, which are governed by the strong force.
Okay, the strong force. That's what binds quarks together inside protons and neutrons, right? It's the glue holding atomic nuclei together.
Exactly. But its mechanics are entirely counterintuitive compared to the forces we experience on a macro scale.
How so?
Well, with gravity or electromagnetism, the further apart two objects get, the weaker the attraction between them becomes.
Sure, like magnets. You pull them apart, the pull gets weaker.
Right. But the strong force operates in reverse. It actually gets stronger as particles move farther apart.
That makes no sense.
I know. The researchers use the analogy of a rubber band. The tighter you stretch the connection between two quarks, the harder the strong force pulls them back together.
Okay, so imagine grabbing two quarks and pulling them apart. The tension builds and the stored energy increases exponentially.
Yes.
And eventually you pull hard enough that the energy required to stretch that quantum rubber band becomes just immense.
And at that point of immense tension, the energy literally converts into matter. It follows Einstein's equivalence of mass and energy.
Oh, wow. So the rubber band snaps.
Exactly. The rubber band snaps, and the built-up energy spawns entirely new particles out of the vacuum to cap the exposed ends of the severed connection.
From a calculation standpoint, that sounds like a computational nightmare.
It is the ultimate nightmare.
Because if you're trying to write an equation for how a muon interacts with virtual quarks, you have to account for the strong force. But the moment the interaction stretches or becomes complex, the strong force spawns new particles,
Right.
which in turn have their own strong force interactions. Wait, those spawn more particles.
Yeah, it just keeps going. It becomes this infinite nesting doll of mathematical chaos.
So that exponential complexity is why accurately predicting the muon's behavior from purely theoretical first principles was considered like the hardest problem in particle physics.
Absolutely. The math becomes intractable almost immediately.
So how did they do it before? Since they couldn't calculate the strong force interactions directly, what was the workaround?
Well, for decades, they relied on collecting thousands of past experimental results. They looked at electron-positron collisions happening in accelerators all around the world.
Okay.
And they essentially stitched this historical data together to approximate the strong force's behavior. That's how they extracted a single theoretical number for the muon's magnetic moment.
But wait, if the strong force is one of the four known forces, shouldn't we have algorithms for this? Why did Fodor's team take more than a decade to figure this out if the force is already known?
Because that data-driven approach was inherently limited. Relying on experimental data from different eras, calibrated on different machines, You are basically baking the systemic errors and uncertainties of those past experiments directly into your new theoretical prediction.
Oh, I see.
To definitively prove whether the standard model was right or wrong, Fodor's team at Penn State had to abandon the historical data entirely. They had to calculate the strong force interactions purely from the foundational equations.
Here's where it gets really interesting. To process the infinite nesting dolls of the strong force, Fodor's team utilized a computational framework called lattice quantum chromodynamics.
That's quite a mouthful.
It is. But basically, instead of trying to calculate continuous interactions in an open void, they discretized space-time itself.
Yes.
They mathematically chopped the universe into a microscopic, multidimensional grid.
Exactly. By breaking the continuous flow of spacetime into tiny, discrete cells, a lattice, they constrain the infinite possibilities.
Okay, so you place the quarks on the intersections of the grid and the gluons on the links between them.
Right. And this allows supercomputers to numerically solve the equations governing how the particles interact from one tiny node to the next.
It sounds like trying to perfectly map the currents of an entire ocean.
That's a great way to think about it.
Like instead of tackling the whole ocean at once, they divided it into millions of tiny swimming pools, calculated the ripples in each one using supercomputers, and then stitched the map back together.
Yes. And it's also similar to how meteorologists forecast the weather. They don't try to calculate the continuous movement of every single molecule of air on Earth.
That would be impossible.
Right. They place a virtual three-dimensional grid over the atmosphere. They calculate the temperature and pressure in 1 cubic mile of the grid, figure out how that specific box bleeds pressure into the adjacent box, and so on.
And lattice quantum chromodynamics does this on a subatomic scale.
Exactly, calculating how the strong force bleeds from one microscopic spacetime cell to the next. But the challenge is the scale. As you make the cells in your weather grid smaller to get a more accurate forecast, the computational power required just skyrockets.
Oh, I bet.
For Fodor's team to achieve the precision necessary to challenge the muon anomaly, they had to simulate the equations using far finer lattices than any previous study.
But if you are using a supercomputer to calculate the microscopic distances on this incredibly fine grid,
Yeah.
and you need to scale that up to match the macro-level reality of the muon, how do you stitch those mathematical models together?
It's extremely difficult.
It seems like blending a purely theoretical microscopic grid with broader physical behaviors would just cause the equations to tear at the seams.
And that stitching process is where the Penn State team employed a highly sophisticated hybrid strategy, sometimes referred to as the window method.
The window method.
Yes. They recognized that lattice calculations are exceptionally precise for short and medium distances. Those are the highly chaotic zones where the strong force rubber band is snapping.
Right.
But as you expand the grid to larger distances, the computational noise builds up and the lattice calculations lose their reliability.
And conversely, the old method of using experimental data is terrible at short distances, but highly reliable for mapping long-distance interactions.
Exactly. So Fodor's team mapped the mathematical behavior across different scales, and they found the exact intermediate window where the uncertainties of both methods were at their absolute lowest.
Oh, that's brilliant.
They used the supercomputer lattice to conquer the microscopic chaos, and at the precise boundary where the lattice noise began to grow, they mathematically anchored it to the highly reliable macro-scale physical data.
So this blending of pure theory for the microscale and established physical data for the macroscale, combined with the finer grid resolution, it completely altered the theoretical prediction.
It changed everything. The amount of mathematics, programming, and sheer computer architecture required to process this hybrid model is just staggering.
And the results of this calculation were definitive. When they ran the numbers utilizing this new lattice model, the theoretical prediction shifted. It aligned almost perfectly with the physical measurements taken by Fermilab and Brookhaven.
Yeah, the 60-year discrepancy just vanished.
The theoretical numbers and the physical experiments matched within less than half a standard deviation.
It's incredible.
Fodor's team confirmed that the standard model of the universe is accurate to 11 decimal places.
11 decimal places. We are talking about a mathematical model predicting physical reality down to parts per billion.
Wow.
And accounting for electromagnetism, the weak force, and the chaotic strong force all at once. It is a towering achievement in the history of theoretical physics.
Truly.
It proves that our foundational equations, when calculated with sufficient computing power and methodological rigor, reflect the physical universe with breathtaking accuracy.
But despite resolving a 60-year mystery and achieving 11 decimal places of precision, You'd think there would be a massive party.
You really would.
But the researchers had a surprisingly muted reaction. The lead author, Zoltan Fodor, actually stated publicly that he felt, quote, somewhat sad about the discovery.
Yeah, the sadness really stems from the psychology of discovery.
How so?
Well, when Fodor's team began this calculation, the entire physics community assumed that a highly precise theoretical calculation would actually widen the gap between the math and the experiments.
Oh, so they wanted the gap.
Exactly. They fully believed they were about to definitively prove the existence of a new fifth force of nature.
Man, they spent a decade meticulously designing a key they thought would open the door to a completely new era of physics.
Right.
Instead, the key just perfectly locked the door they already had.
That's exactly it. They proved the fifth force isn't hiding in the muon's anomalous magnetic moment. The established forces explain the wobble completely.
So what does this all mean? Is this a letdown for the listener? I mean, we love a good mystery.
We do.
If the standard model is totally unbroken, does that mean physics is essentially done and there's nothing left for us to discover?
If we connect this to the bigger picture, physics is nowhere near finished.
Okay, good.
The standard model, for all its 11 decimal place perfection regarding the muon, it still has glaring blind spots.
Like what?
Well, it cannot account for dark matter, which makes up the vast majority of mass in the universe.
Right, that's a big one.
Huge. It cannot explain dark energy, which is accelerating the expansion of the universe, and it completely fails to integrate gravity at a quantum level.
So the global scientific apparatus, including the U.S. Department of Energy and the European Research Council who supported this research, they will definitely continue searching for new particles and hidden forces.
Oh, without a doubt. This specific calculation simply removes the muon's magnetic moment from the list of reliable clues pointing toward that unknown physics.
That makes sense.
And there is profound value in this kind of verification. The human desire for a new mystery shouldn't overshadow the majesty of what has actually been accomplished here.
Definitely.
We have developed abstract mathematical formulas that can predict the behavior of invisible particles, interacting with virtual ghosts in a vacuum with a precision of parts per billion. The fact that nature actually follows the rules we deciphered is deeply beautiful.
It really is the ultimate validation of human reason. The rule-breaking muon wasn't breaking the rules at all. It was just exposing the limits of our own math.
Exactly.
By combining colossal supercomputing power, space-time lattices, and sheer persistence, scientists proved our foundational understanding of the universe is astonishingly accurate. And for you listening, whenever you feel overwhelmed by a complex problem at work or in life, remember that breaking it down into a grid, just like Fodor's team did with space-time, can actually solve the seemingly impossible.
That's a great takeaway. And I'd leave you with this to chew on. Think back to that strong force rubber band we discussed, where sheer energy stretches until it snaps and creates entirely new physical particles out of empty space.
Right.
If the empty space around you right now is constantly boiling with ghost particles popping in and out of existence, subtly pushing on everything, how much of what we consider nothingness is actually the invisible machinery holding our universe together?
Wow. It changes the way you look at the space between your hands. The fundamental rules of the universe remain intact, and the math finally balances out, but the invisible mechanics keeping that balance are wilder than we ever imagined.